All right, so welcome everyone. My name is Vaibhav. I'm a product manager for Cloud GPUs, and I work closely with the PyTorch XLA team here. I think most of you we have met in PyTorch sessions yesterday, and for those of you who I have not had chance to meet, so welcome. And in today's breakout session, we are going to talk about PyTorch XLA FSDP. That was sort of the original topic of this session. And then in yesterday's talk, yesterday we had a talk on SPMD, and there was a breakout session afterwards. And there were some interesting sort of questions related to performance, partitioning, and so on and so forth. So I thought that maybe I'll just connect those two dots and talk about both FSDP as a specific approach that we developed a few months ago in PyTorch XLA ecosystem, and then tie it with SPMD, which is our latest and greatest addition in terms of the general purpose ability to express any kind of partitioning for your large models, and then make some connections into what are some of the best practices and how to think about performance for these different approaches. I have a few slides, but I want this to be very interactive. This is a breakout session, and I'm only supposed to speak for 20 minutes. I don't think I can finish in 20 minutes what I plan to share, but the core of the session is discussion. So please feel free to ask questions and comment, and as lively the better. Okay, so I have a high-level agenda. For those of you who may not be familiar with PyTorch XLA to begin with, I just will have a quick sort of introduction to get get you the intuition of how PyTorch XLA work a little bit differently. And although from the usage point of view, it maintains the user experience of the core PyTorch, and in what way then we add all these amazing capabilities to PyTorch and then solve interesting problems. So then I'll go to PyTorch XLA FSDP. XLA FSDP has been and also SPMD has been work of many great people within and also outside Google. Particularly XLA FSDP was one of the contributions from a friend of mine from Meta AI. So he's not here. My uh, my goal originally was for him to do the talk, but he said that he was not able to make it, so I decided to do it myself. Okay, so then we're going to talk about FSDP, and then we will move into performance and think about partitioning and all these other things, and how to like have some general templates when it comes to SPMD partitioning, and then how to apply these templates, and when you're applying these templates, how to make sense of the performance, how to look at the profiles, and make sure that it's actually doing what you intended to do, and if something is going wrong, how to spot that essentially. I had intention of adding some potential optimization opportunities. If the time permits, we'll go there. Okay, so let's get started. PyTorch XLA, lazy tensor. So lazy tensor was that original sort of concept which was used to build PyTorch XLA, and since then there have been many things. Like, for example, sometimes people think about Dynamo versus lazy tensor, but in its core, in its fundamental, it is the same approach, that there is a tensor on which you're doing a set of operations, which operations are recorded and only executed when required or when forced to be executed. So here is a brief graphic. Sorry.
If I say a few words here?
Yes, Milad, please.
There's this dichotomy, just wanted to kind of demystify it, that we've heard a bunch of times around like lazy tensor versus Dynamo, and I think that's what you were referring to.
Yeah.
So when it comes to the PyTorch upstream, there are two ways of there are two execution patterns that you could observe as PyTorch kind of generates ops and passes them down to be dispatched to backend. There's a Dynamo path, which is what they introduced in 2.0, and the other path is the non-Dynamo, which is more of a legacy execution format that PyTorch has been carrying for. Either way, PyTorch XLA goes through its stack, which is historically called lazy tensor, and processes them. So in a way, I just wanted to kind of call it out and make sure that people realize that these are two different levels of the stack, and they're not like one versus the other. It's like there's a Dynamo path, a non-Dynamo path. either way, like the tensor is able to handle them at the PyTorch XLA level and and produce the offset that is necessary for XLA to move forward.
Thank you, Milad. Yeah. So with that background, here is a simple code snippet, and this is just to drive home the spirit of how lazy tensor works. So this is the example code where I'm creating two tensors. There is XLA device abstraction, and then I'm transferring these tensors to the XLA device, at which point they become the XLA tensor, and we'll have some interesting properties. So what I'm showing on the right-hand side here now are these sort of the visual of these two tensors being created. Then I'm going to add an operation on these tensors. So this is a matmul operation between these two tensors. Notice that this operation has not been executed yet on the PyTorch XLA device. So which means that this is like what I'm showing on the right-hand side is sort of abstraction of the graph or the computation graph being recorded, but the operation itself has not been executed. So furthermore, I can go on doing these things, and you have the APIs to view these graph in the PyTorch IR or the XLA HLO format if you wish as well. And as you can see, as I go on adding operations, the graph basically just builds and reflect those new operations as well. And one example of when it is forced to execute is running into an op that has no XLA lowering. So in this, at the time of creating these slides, which is months ago, Unfold was an op which did not have lowering, but since then I'm sure there is lowering for this op, but this is just for the illustration purposes. That I'm assuming that there is an op which does not have a lowering, which is encountered in the code, and when it is seen, then what PyTorch XLA will do is that it'll cut the graph leading to that op and then lower it into HLO and then subsequently compile and execute it on the TPU device. So for those of you who were there in the session, someone asked the question like, what is the stack, how it works from the PyTorch layer all the way to TPU. So this is very, very high level, but still some helpful abstraction to know about. So once the execution has been done, you would notice this tensor by2, which was leading into that yellow blob, which did not have a lowering, has been materialized. So there is another term that light tensors versus materialized tensors. So until it has been materialized, these are all were light tensors. And once it has been executed, then we call that the tensor has been materialized, which means that we know the value of the tensor. And now once we know the value of the tensor, we can sort of have this device to host, and then followed by that, now the this op itself, the yellow blob, can be run on CPUs because all the values feeding into it are known at this point. And then the tracing continues in this way. So this hopefully gives you a sense of how PyTorch XLA at a conceptual level works. Now, since the session is about FSDP, and I also said we were going to talk about partition later on, so it is useful to refresh some foundational parallelism strategies here. So I'll just focus on data parallelism, and happy to go into some tensor parallelism examples as we dive in there as well. So what I'm showing here is this canonical two-layer dense neural network. This basically happens to be one of the it looks very simple, but is one of the sort of important building blocks of your transformer. So this is your feed forward layer. And when we all did that first course in neural network, we just looked down upon these two back-to-back dense layers. But turns out that it is very important, and very advanced transformer architectures like mixture of experts and so on and so forth actually make very sort of intelligent use of this boring two-layer component. But again, focus of the talk is distribution. So what's going on here? So the graph in the middle is sort of the high-level computation graph. So there is X, there is W1, there is matmul happening, there is a hidden vector that is generated as a result, and there is another matmul which generates the output. Fair enough. And once we do the data parallel, or what PyTorch likes to call the distributed data parallel, essentially what we are doing is that each replica or each rank where the computation needs to be performed will hold this entire graph. And this then is going to work with some different values or set of values for X to then execute this graph. Fair enough. So there is load model, forward, backward, all reduced, weight update. This is what your DDP looks like. When we move to FSDP, however, some very interesting things happen. And one of my friends, and I think he's not the only one to call it that, FSDP is a sort of disguise for model parallel. It is actually a model parallel approach. But that being said, it is, again, not the debate that we will go into today. But what we are doing in FSDP is that we are making sure that each replica itself is going to work with a shard of model parameters. So since it has only the shard of model parameters, in order to do the forward pass, it has to do the all gather on the shard that it holds. Once it has the all gather, then it has the whole parameter for doing whatever computation needed, then it can do the forward pass. And once the forward pass is done, it has to release the weights. And the emphasis, or one of the core objectives, and there are many benefits of FSDP, but one of the core objectives were to reduce the memory footprint for doing something which is exactly same as your regular rate of parallel without adding new computation cost, and we are able to achieve that using this fully sharded data parallel approach with reduced memory footprint. Again, nothing novel here. Both Microsoft Research as well as Google, there was a lesser known paper called Automatic Sharded Weight Update. If I'm remembering correctly, you can Google it, and that basically goes into the same approach, essentially decomposing all reduce into all gather and reduce scatter, and then pushing all gather in the back of the loop so that now it looks like load the model, wait all gather, do the forward pass, then release the weights. And optionally, you do that wait all gather in the backward pass because you can choose to keep the weights for the backward pass as well. And then do the reduce scatter. So the sort of averaging of the gradient is happening only for the shard that a specific replica holds. Okay, so this is the fully sharded data parallel, very well-known technique across the world. I think, pretty much, I think there is no large model trained which is not using fully sharded data parallel somewhere in some form. And even if you're using other techniques in conjunction. Great. So with what we call the user mode FSDP or XLA FSDP, this was the first approach that we added to the PyTorch XLA library, which basically allowed people to scale to really, really large model sizes using XLA FSDP technique. There was really no limit, and there's a blog post that we also published which showed result up to 256 billion parameter model, which could be trained, and again, leveraging the same technique that each rank is holding only the shard of weights. And there are some really interesting things that you can do depending on at which layer you do the FSDP wrapping. So what I'm showing on the right-hand side is that's wrapper-based approach, where there is, and this is exactly, or I should say very similar to how PyTorch core FSDP works, is that there is an FSDP wrapper, which you wrap around a module, and whichever module you wrap this magical wrapper around, will have its module parameter sharded, and its forward and the backward will be modified similar to what you saw in the previous slide. Okay, so this is what we do. We could do the 0-2, that is optimizer state and parameter sharding with this approach, and we could also do this nested FSDP. So therefore we take it to the 0-3 kind of optimization. And again, there are other techniques like gradient checkpointing, or it should be better named activation rematerialization, because that's what it is. But for some weird reason, people call it gradient checkpointing. And so essentially, this is again a wrapper-based approach, sort of extending the core PyTorch gradient checkpointing capability into PyTorch XLA, and does the same thing. If you wrap a model with a gradient checkpoint wrapper, essentially activations inside that model will be recomputed during backward pass instead of being saved, essentially. Needless to say, you can combine this user mode FSDP and gradient checkpointing and do nice things. And this is what we also published in our blog post, which was able to get some really interesting scaling and optimization results as well. Now, I think if I go back to this diagram here, all this is great, but the desire for distributed computing in general, or for large scale training in particular, is to hide these communication operations. If these are sort of exposed, and there was a nice term someone says that the tail is tucked or not. So this is a tail that we want to tuck. And if we can tuck the tail, then we are better off in terms of our overall efficiency. And the extent to which the tail is not tucked, we are paying some penalty for the distribution. So one of the key sort of fundamentals there is this whole FSDP wrapper itself is written in the user space, so to say. This is not compiler driven partitioning approach, which is that someone actually decided to shard parameter, and there are some interesting tricks that we had to use in order to then manage the memory, make sure that whatever is being manually sharded is actually not destroyed by compiler optimizations and so on and so forth. And then there is, of course, a better way, and we'll talk about the better way as well. And you have already seen the better way yesterday using SPMD. So just to pop that bubble. But there is a lot to unpack there, and we will build upon what you have seen yesterday. So what is going on here is that first thing is that in terms of difficulty, since this is happening in the user space or user mode, the collectives are inserted and exposed, so they are not overlapped. So this is why if you will compare the user mode FSDP to a compiler implemented FSDP, you will see that compiler implemented FSDP should do better if you have done everything correctly there. Second approach, the second sort of difference is like, for example, in terms of memory handling also, because you're trying to do something which is very outside what is in the typical programming model of XLA. That the typical programming model of XLA is you express computation, you share your intent of partitioning, and compiler is going to do all the heavy lifting for you. And there you are sort of thinking, okay, I'm going to do something more elaborate myself, which finally we were able to do in this case. And for example, limitations such as not the similar direct access to the tensor storage, so that you can free up those storage and so on, was addressed using some other techniques by changing the reference to some dummy scalar and stuff like that for releasing the parameter memory. Needless to say, it was not a straightforward project to do. So kudos to all the people who actually made this made this happen. Jack just in time left because he knew that I was going to say kudos to him. and Ronghang, who is not in this room, is of course the core contributors, and this team here. I think everyone helped to make this happen. Okay, and then another sort of common issue, and this is conceptually something to keep in mind, which is helpful, is that XLA, among all its optimization abilities, benefits from looking at the computation graph in a bigger chunk and then optimizing it. So and this is why most of the time you're not found in the business of writing XLA kernels, although this capability is also sort of slowly developing, and it will be more and more prevalent when people want to do something specific. But the TLDR is that, like, unlike, for example, for non-compiler based approach, there is a computation, there is some kernel which knows how to do this computation on a specific hardware and is dispatched asynchronously, efficiently, and so on, leveraging that hardware. Now, the bigger the scope of this computation, more optimization opportunities you can identify. And to name a few is opportunities such as fusion, which can reduce the trips to HBM, and opportunities such as computation communication overlaps, which basically is only possible if the sort of dispatcher, so to say, for lack of a better word, who is looking at this computation has this global view. And this is where XLA compiler is a very effective approach. So although with that approach also seems that if you intentionally try to introduce collectives and release memory and so on and so forth, if you do not introduce barrier, then it will kind of undo the work. Maybe someone needs to let them in.
It's behind her.
So this is why it is helpful to know about optimization barrier in general. So although we did use it for XLA FSDP or the user mode FSDP that I've been talking about, but in general, there is such a thing called optimization barrier, which you can use to kind of break the chunk which XLA is going to optimize over or against. Okay, so I've been sort of hinting at it, and you have heard from Yono and team yesterday about the gory details of XLA SPMD, the API, and so on. I'm not going to focus on the API itself. I'll just focus on some of the conceptual sides of partitioning itself in context of SPMD. So just to sort of set the background or the the basics out there, this is from our XLA SPMD blog post. So in order for SPMD to work, there are two pieces that you need to specify. One is that you have a set of devices. Doesn't matter which topology, doesn't matter what is the underlying interconnect, but you have a set of devices. And what you want to do is that you want to create the logical mesh corresponding to the set of devices, which I'm referring to the physical mesh. The mesh is not a requirement. At the end of this logical mesh, essentially what I'm identifying are two axes. It could be 3 axes, it could be 5 axes. These are the 3 axes, or essentially three ways of creating collection. So for example, if you see in this diagram here, there is this blue marked square, which is basically representing these 4 bubbles, which are the edges or the corners of that square. That represents a chip, essentially. And what I'm trying to do is that I'm trying to create a group, which is these 4 chips, essentially. If I have a physical mesh that actually has those edges as ICI and so on and so forth, then I benefit from those mesh as I'm trying to do collectives. And what I will do here is that I will benefit from the 2 axes instead of just 1 axis of those connections. So at the end of the day, even if there was nothing existing between them, I could still make that group. I could still do collective operations, and depending on what is the characteristic of my physical system, I will still be able to run those collectives hopefully efficiently. And what we are doing here is, although it has its basis on TPU systems, but it is not really tied to a TPU system concept, and you can apply it for other kinds of systems as well. So the logical mesh, as we have created now, it has these 2 axes, which are arbitrarily, by the way, and mark the choice of word, which is arbitrarily called model and data. There is nothing inherent to model and data parallelism on the axis names itself. You could call it X and Y, you could call it MPDP, you could call it Rajesh Vaibhav also as the 2 axes. And then there is sharding annotation. So the sharding annotation itself is going to make use of the logical mesh, because what I'm going to say now is that I'm going to express my intent of sharding for a tensor. I'm going to say that here's a mesh, by the way. As you think about partitioning these things, these are the 2 axes that you should know about. And then I'm going to say axis 0 of the tensor should be sharded across data parallel axis, and axis 1 of the tensor should be sharded across the model parallel axis. This is just an arbitrary example. So essentially, sharding annotation is what we need. In order to come to sharding, sharding annotation, I need how I want to partition the tensor, and along what physical axis these partitioning should map, and that is what is expressed by the logical mesh, essentially. And then XLA compiler does the magic, and you benefit from it. Okay, so just to make things more complicated, I am going to apply this concept into a decoder layer. So that is the building block of a transformer or transformer-based architectures. Typically for decoder-only language models such as GPT-3 and PALM and so on, essentially this is a stack of decoders. And there are details in terms of attention mechanism and so on that can change. I'm not trivializing the work itself. This is, of course, very impactful, and we all by this time know it very well. But from computation point of view, this is the building block. And thankfully, this is very, very standard. And what I'm showing here is that, and thank you for your compliments on the choice of colors here. I I could have made it better, but the light blue here is what is activations. The white ones are the weights. So I'm starting with an input activation to a transformer layer. Then I go to weights. So the first set of weights is the QKV projection weights. And then there is, once this activation gets multiplied by the projection, then we have the actual projection, which is an activation. So that is the QKV projection. And then there is attention weights that is generated by doing the dot product of query and key. And then there is normalized attention weight, which is another activation that is generated, which is almost a copy of that. Then there is a scaled value, which is essentially based on the value you're doing, the element wise scaling of the weights that you have generated with the query and key. And then finally you have attention output weights, and then there is an output matrix at the that is the last parameter of your self attention module. And then you have WI, that is expansion, and some people call it projecting up and projecting down, or expanding or contracting. So this is basically WI and WO. Typically, it is 4 times D model, so that is the assumption in this table, but doesn't have to be. So the second column here lists down the dimensions, which again, very, very standard. No matter what is happening, these are the dimensions that you have. And then we have some interesting ideas in terms of partitioning. Which, by the way, if you look at it, then you would think that maybe it is. If you look at it long enough, you would say that it is common sense. But if you're not looked at it long enough, it's not. There is a question. Oh yeah, thank you.
Yeah. But
Amit?
Amit, so I had a quick question. So before we go, because this is a correct slide. So you mentioned 2D parameter, 2D activation. That two-dimensional from your previous slide, does it refer to the data and the model parallel? Is that what means by 2D? One is the data parallel, another one is the model. Like if you go to your earlier slide.
Yeah.
So
So
okay.
So answer is no. And so here is why. So the axis of your logical mesh are the means to express partitioning. That's it. So there could be a third axis here in the same diagram, which is called MD, for lack of a better word. And then when I come here, what I'm specifically calling is, notice the dimension of each of the tensor. And you would notice it is called DP, none, or MP. And this DP, MP could be AB, could be XY, whatever it is. So if you look at a column which is 2D activation, 2D parameter sharding, each of the activation tensor has at least 2 axes or 2 dimensions, which is being sharded. And each of the parameter tensor has 2 dimensions, which is being sharded. So irrespective of how many logical axes your logical mesh has, this is the partitioning intent. So the numbers that I'm using here, for example, if I go to 1D activation, 1D parameter sharding, and this is essentially what was introduced in the first Megatron paper. And if I go to WI, WO, I think you will recognize this really, really quickly. So WI has the partitioning intent of none, comma, MP, and MP, comma, none. Forget about MP. You would remember, if you look at that paper, it has the column parallel linear layers and row parallel linear layers. And the column parallel linear layers were used for WI, and the row parallel linear layers were used for WO. Exactly the same thing. So I am only only sort of partitioning one axis, the column, and for WI, and one axis, the row for WO. Does that help, Amit?
Yeah. So basically those two correspond to the last two columns. The 1D parameter, basically. 1D parameter is like a row parallel, or it can be row parallel or it can be column parallel. But you're doing
Yes.
only on one dimension.
Yes. Yes.
I see.
Yes.
So the 2D is like you improved upon that, and then where you're using two dimensions instead of one dimension to shard.
Yeah. Yeah.
Okay.
Yeah.
Okay.
And in yesterday's session, I just also referred people to read GSPMD paper, which actually goes into the whole gory details of all kinds of partitioning, and basically arrives at that the 2D activation and 2D parameter can be called 2D sharded version, and is also called fully sharded. So this is basically saying this is the maximally we can shard the computation. Characteristic is that what is sharded remains sharded until and unless it has to do something that requires all gather and so on, it remains sharded essentially. And it has a very, very special, like easy to identify, computation and collective pattern that I will talk about shortly, which you can see in your trace, and you can see that yes, I have done it correctly. You have a question?
Yeah, question. So you said it doesn't matter DP or MP, right? But does it matter, like, how do you choose which of the dimensions is DP, MP? Does that matter? Is there an optimal?
Yeah, I think this is a
Is there a combination that
this is a this is a good question. So what you're seeing here is kind of a recipe which has come out of a lot of people did a lot of work. They come out of this, and this works basically. Now, in terms of how to choose that, Megatron paper does a very good job at that. Once they introduce the row parallel, column parallel linear layers, they will actually have it. They have an example where they say that what if we sharded the first matrix row wise instead of column wise? What will go wrong mathematically? So they actually explain it. And then one more useful intuition is that for consecutive layers, it works like conjugates. So if a column is partitioned, then for the next one you have to partition the row. But again, I'm not doing justice to it. Megatron paper does a good job at it, and GSPMD does a good job, but it is hard to digest paper. So yeah.
If I may add, like, just one small point to what Vaibhav said. If you look at that way, the activations are sharded in the 2D activation, 2D parameter sharding. If you perform the matmul, where the weight matrix is sharded on the column, your activations are naturally going to be sharded along the last dimension. So it makes sense to shard the activations along the last dimension because it's naturally going to result in that sharded way, and the sharding propagates sort of. There won't be any computation. But instead, if you use another axis, maybe you'll have to change because you're forcing the compiler to change the axis. You'll incur some communication maybe, but it naturally results in the activations being sharded in this way.
Yeah.
Yes.
Yeah.
So
So-
for every model, there's a ideal recipe
No.
mathematically.
No,
right?
no, that is not. So it is thankfully not for every model. It is essentially if you identify certain building blocks, and easiest one is two-layer, MLP, right? And you really understand it, like what is going on here, and we will actually dig into a lot of details there. Then you can apply this in different settings, because what will happen is that you will see patterns of two linear layers happening in some places. By the way, this is not the extent of what XLA compiler can do. It can do any goddamn sharding that you can come up with, it will do it. But then if that is not done correctly, what it will try to do, it will try to gather things that you don't want it to gather. It will lose time in the process, and it's not going to work well from performance perspective. However, there are things like, for example, spatial partitioning, which is a completely different concept altogether, right? Where you are partitioning your it is usually used for vision context, where you're partitioning working with the big pictures, for example. So when you partition along X and Y, dimension, then all of these things nicely are propagated by the XLA compiler, and which is the whole value of the SPMD. And I think in the GSPMD blog post, we also show some results of using this for spatial partitioning. So it's not just transformer, but this is well-studied area, pretty standard recipe. We do not reinvent it every time. If new attention architecture comes, we don't care the less. And yes, of course, there are optimization in terms of for long sequences, things like flash attention and so on and so forth. So those have a different line of work, and for maximal control, you may want to write a custom kernel for XLA, and that's not like fully paved for the PyTorch XLA yet, but very soon it will be fully paved.
Maybe just to add to that.
Oh yeah, there was a question. Sorry. Yeah.
Yeah. I have another quick questions. Maybe you will cover this in future slides. So so you're sharding parameters and activations, correct? Now, what do you all gather? Do you all gather, like, let us say in a forward pass? Do you all gather the activations again and the weights, or what will stay in place, and what do you all gather
Yeah,
to do
that
a
is a
forward
very
pass?
that is a very good question. And the next slide, we'll talk about it. You have a comment.
Yeah, it's a quick comment, like regardless of what kind of attention implementation you actually swap into your transformer-based architecture. And if you focus on the input and the output of that attention layer or the block, then you can still, go with this recipe.
Yeah. That is a very good point. So, which means that the core feature of XLSPMD is that you actually don't have to define all of this. You can define a handful of annotations at the beginning of the attention block, and the rest can be inferred by the XLA compiler. However, knowing what it should be is helpful to debug, because if you don't know what it should be, then you're looking at a trace and you have no idea that is it optimal? Have I optimized? Like am I doing what is the state of the art? How do I know? So and this is why it is useful to know, and this is why sometimes you also do over annotation, which means that even though you know that XLA will infer it, you go and write an annotation there and say that I would like this tensor to be sharded, which sometimes also helps XLA compiler for it to know that, okay, so this tensor needs to stay sharded. So if something is asking me to all gather it, I will not do it. Essentially.
There was some finding that we had on the input charting versus output charting. Maybe you wanna basically what we discovered about output charting and kind of like pinning down the output to make sure.
Oh, sure. So like, one of the important aspect of like 2D sharding is that like you not just shard the parameter, but you also need to shard the activation, the output of the memo, so that you make sure that like, cause like if you don't shard the activations, there will be a tons of alternative that the compiler going to infer about how to shard the outputs. And then if you want to achieve the best performance, you want to say you want to like pick the one that fit your scenario the best, and then enforce that, and then the compiler will do will insert the right collective to make sure that after the results are produced, that each device will still have the exact local shard that you expect to have. Yeah, so that's one very important lesson we learned. And then we only need to do that for the forward pass. And for the backward pass and then the optimizer step, the compiler will actually can inference, like can propagate that very correctly for us.
Yeah, and aren't we all grateful that we are actually not have to go and chart the backward pass ourselves? Like,
Yeah.
who here is grateful for grateful to XLA compiler for taking care of that charting? Yeah, Amit.
So I had a question. So why can't we make this a default? Like, if it's a mat mult, why can't we make always the output sharding as a default? I mean, is there any case where
Well-
where it otherwise helps, like, and then that way we would have solved the configuration. Yeah.
Amit, there's something to be said here. There is some room for flexibility and control, right? Like I think what Wipop was saying was mostly like, hey, you have a lot of control, and then what Gio isn't saying is that, well, you can actually what Wipop's point is there's a lot of flexibility, but at the same time, if you want to control it to a specific target, then there are some knobs for you to apply. So you can be more flexible or not, depending on your use case and the requirements around how much sharding annotations you want to apply. Hopefully, we'll get to a day where SPMD is just so smart and so advanced that you don't even have to put any sharding annotations in.
Yeah.
Well,
You
they're,
said
they're
that-
not there
That's
yet,
the,
realistically, right? So, and it'll take a while.
Yeah, and I will move to the next few slides in the interest of time, because otherwise we will run out of time. And I think Amit had a question which will hopefully be covered here. So what should it look like after all this MP-DP business? Like, what should it look like? So again, going back to the two-layer MLP, which is which is easy to understand. Everyone can grasp what is going on. Two dense layers. So what I'm showing here, I'll just decode the terms here. So this is transformer MLP. So this which means there are two weights, W1 and W2 here. If you can see my cursor, let's see if you can see my cursor here. Great. So you can see this is the first weight and this is the second weight. The dimensions of this is also important. So this is M by F and this is F by M. So M is your D model dimension and F is your FFN dimension, which is typically 4 times D model. Okay. The colors mean the colors refer to the axis of partitioning. So red is, again, like I was saying, MPDP is just a label for the two sort of axes there. So what's happening is that F means this is the dimension that stays sharded on the red axis. Blue means this is the dimension that stays sharded along the blue axis. And so as you can see, what we are starting with is a sharded activation, which is sharded weight, which is M by F. And when I say sharded weight, which means that the first dimension of this weight was sharded along the blue axis, and the second dimension was sharded along the red axis. And what we are doing here, the blue all gather, AG is the all gather and RS is the reduced scatter. So the blue all gather is doing the all gather along the blue dimension. So what I'm doing here is that I'm only doing all gather along the first axis and not on the second axis. And as a result, that blue M gets converted to black M because it has been all gathered. And the red F remains red because there was no all gather done there. You will see that there is a certain sort of conjugation pattern here, like if you note like how the blue and red go together. And what is happening on the second branch, this is the output of the self-attention block, which is batch times sequence length times D model. Again, pretty standard. Whatever people are doing inside attention block doesn't matter. This is what it will look like, right? Of course, there can be a new architecture which has done something completely radically different, but it will still be a helpful mental model to have. So once again, I think you can decode the rest. I'm doing the all gather on the red axis there. And then there is a matmul. That is the first matmul, which is with W1 and the first activation here. And then there is a second matmul that goes on with W2. And again, you would notice that all gather that happened on the blue axis are on alternate axes of the tensor. So this is happening on M, this is happening on M, but M itself is conjugate. So just think of the conjugacy concept that we were talking about from the Megatron paper. So if you have implemented your 2D sharding correctly, which is what we recommend in general for the scenarios which are and there is a specific recipe I'll try to derive somewhere in the talk. If I don't get there, then here's the recipe. Recipe is that if your number of tokens per batch is much greater than your D model, then you're better off using completely fully sharded along all the devices. Don't even think about tensor parallel. But if your D model is much greater than your number of tokens per batch, then chances are you would benefit from using tensor parallel on one axis and fully sharded data parallel on the remaining axis. And this is what we are doing here. So this is an ideal recipe for the scenario where the D model is much greater than the number of tokens in the sequence. Now, this is not voodoo magic. There is a proper mathematical explanation for it. We'll come to that. Okay. And I think from this base, now it becomes easy for you to create all other variants. If I ask you that, okay, so what should it look like? What should competition graph look like for 2D parameter, 1D activation sharding, 1D activation, 1D parameter, 2D activation sharding, and you can derive the rest. So I'm not going to go into all the details there. As you can see, I can go from one to the other pretty easily. Yes, Amit, you have a question.
Now, one very quick question. So is this similar to the sequence parallelism in Megatron, the way the activation sharding you're showing? Is that similar to that, or is it slightly different? I mean, the way it's implemented. If you look at the sequence they also kind of shard the activations along the TP dimension. Is something similar to that, or it's different?
Yeah, I do not recall sequence parallelism
Okay.
in the Megatron paper, so I will not be able to
Okay,
comment
that's fine.
accurately. Does
Yeah.
Like if you can say a few things about, like, is it pipeline parallelism? Is it
No.
terapipe like parallelism? Is it pure tensor parallelism?
So what they do is they take the sequence, right, and they basically token dimension, and they chop it into the number of partitions as your TP dimension, and they do reduce scatter and again all gather of the activations. So maybe it's similar. I think the idea is similar, but I think maybe you may be doing it in another dimension, like not the tensor parallel dimension.
Yeah.
mean-
As you can see that, like in none of the approaches described here, we are not touching the T dimension. And
Okay.
this is the sequence dimension that you're talking about.
Yeah.
There are interesting approaches to partition along sequence dimension. The one I am aware of is published in you can look up terapipe paper, but that looks like pipeline parallelism in some sense. So what you're describing looks like that it is still done in the tensor parallelism realm, and I would be interested to know about it.
Yeah. Sure. Thanks.
Sure. Okay, so great. So all this is great. Now, if you actually look at the real profile, then you will be able to tell that whether the intent is implemented correctly or not. You also have a recipe that if your D model is much greater than your tokens per sequence, then 2D full 2D sharding is the way to go. And other things are, you can try and see something else.
Just a quick question regarding the recipe. You said if D model is much greater than number of tokens, is this local number of tokens or global? Because let's say you have let's say you have a batch size of 2 samples per chip, and you're using a context length of 4096, then that is 2 into 4096, which is 8K. So
Yeah.
if your emitting dimension is greater than 8K, then TP helps. Is that it?
Yeah, so answer is it is the global number of tokens. So tokens per global batch. And you're comparing it also with the D model, which is global. You're not comparing with the sharded D model also. So yeah, that's the way to look at it, and hopefully we'll get there. It's in the next slide. So you may have did we show this yesterday as well? Yeah. So this is sort of the summary synthesis of some of the out-of-the-box advantages that we can get by using SPMD. One critical thing to point out, though, this is really interesting, everybody. So we're doing this all gather here, right? The blue all gather. You would notice that this is the all gather on one axis of that tensor. So if you Google collective matmul or I think Google has published this paper as well, where we have a really ingenious method of doing all gather matmul in such a way that basically if you decompose all gather in terms of the essentially, async send receive operations. So you can completely hide the all gather with a matmul. So which is extremely useful. So the efficiency comes from hiding or tucking the tail. Essentially, that's the last mile that Shaheen was talking about yesterday. That once you, because all these recipes, this will propagate, things will work well. But not only XLA compiler does that, but also can insert those automatic compute communication overlap. And what I just said, collective matmul is just one example of that. And that is specifically a technique you can use to hide one axis all gather behind a matmul, essentially. Okay, so and then these are these amazing results. Again, kudos to the team here. And now we're going to
Quick question on that previous slide. Isn't it theoretically the FSDP, if you did it right, you could get the same performance as SPMD or no?
That is a very good question, right? So I think the whole theoretical performance piece will go back to the recipe, which is that if your tokens per batch, let's say this was working with a D model of 2K. I'm just making this up. I don't know. I don't think there is a model with D model 2K that anyone is using. Llama 7B is using 4K D model, if I remember correctly. But imagine that you are able to somehow work with a really, really large global batch size for that. Then what happens is that you are better off using FSDP for that specific model. But if you go GPT-3, so 12288 D model, then that is essentially 12,000 tokens. Then your and with that big model, because of activation and other things, this also limits your batch size. So this basically forces you in the regime where you cannot fit a lot of tokens in your batch, and therefore you're better off using tensor parallel.
I had a quick question, Weber. So for this graph that you're showing, the bar. So here SPMD, is it with 2D partitioning? So which style of partitioning you use? Did you like the 2D for activations? 2D
It is 2D partitioning, correct?
Yeah, 2D.
I see. So
Yeah.
basically that means it is not similar to FSDP, right? So it's different, right? With
Huh?
2D partitioning, 2D SPMD is not same as FSDP, if I understand correctly.
Yeah, it is. Yes, it is certainly not same as FSDP, and it has advantages just because it is 2D partitioning, and also because it has automatic computation communication overlap that XLA can do, which is
I
not there
see.
in the FSDP.
Essentially.
I think the
And also
whole,
the
sorry, I think the point of this plot comparing as SPMD 2D sharding against the FSDP is that just to highlight that FSDP has been sort of the state of the art sharding distributed strategy for us before we were able to enable 2D sharding with SPMD. So just to show that with the more advanced sharding strategy, we could actually push the performance further. So it's not to compare that FSDP to FSDP in a different framework.
I see. And also what's the global batch size here actually? Like, what was used here? Do you remember? Weber? Or I know your knowledge.
Yeah, I can look it up.
Yeah,
Okay.
I actually don't know.
What
So
was the question?
The global batch size here.
So yeah, the global batch size depending on different models. Which model were you interested in?
Let's say
Like,
7B.
yeah, 7B or 2B. Yeah,
Yeah, for the 7B, the global batch size, and it will be 256.
or 256.
And
Okay.
then yeah, and then it's running on like V432.
Okay. Thanks.
Okay. So and furthermore, then basically in order to come to the ratio that I was, describing earlier, the D model much greater than the number of tokens. Like, why is that the case? So here is a way to kind of derive that intuition. So what I've done here is that I've listed the, in case of 2D sharding. So this is the same column that you saw in the previous table, that is 2D sharding. I've listed the DP communication and MP communication. And again, this is communication on a certain axis, essentially. And what is happening here is that, for example, and this is all gather, reduce, scatter operations. This is for the MP axis, this is for the DP axis. And if you analyze this is again mapped to all the whole notion of assuming a ring, and assuming, for example, here what we are doing is that for the DP communication, I'm looking at this axis, which is the second axis, which has the width of the D model, essentially. So essentially the DP communication cost will be proportional to D model times DP minus 1 divided by DP. This is the typical ring all gather communication cost that we all know about. Like this, twice of this is basically all of these. And if you jot it down for all of these communications, then you would notice, and by the way, where I have listed as blank is where no communication happens. Like that remains sharded in your 2D sharding situation. So this shows that, for example, the DP DP communication is has the D model square multiplied overall in terms of the overall cost, and the MP communication has this batch times token sort of multiplied to D model. So if your batch times token is much greater than your D model, then your MP communication cost will start to dominate, and therefore you are better off not doing that MP communication, and that's why we say that the fully sharded data parallel. And likewise, if your D model itself starts to dominate, then you're better off splitting it in the way that it's described here. So that is the intuition behind that recipe. So with that, I think we are over time. I took way more than 20 minutes. So are there any questions?
Yeah, I got a question here. So basically, I know you say 1D or 2D shard, but some model architecture is a little different. For example, MQA, GQA, right? The KV is smaller versus the dimensional than the query. I want to know how you handle that. Basically, you can't just shard the same slices as on queue.
Yeah.
So how do I really know what's going on there?
Yeah. So this is a very good question, and so we have to zoom out a little bit and see that in the whole transformer architecture, like there are two big pieces. There is self-attention, and there is fully for FFN layer. So between these two, computation itself is majorly dominated by like the dense matmals, which is dense weight matmals. So if you see, refer to the floating point operations computation across the board, then you would notice that all the dense parameter matmals is of the order of D model square, and the activation matmal within the classic self-attention module is of the order of sequence length square. So plus there is a linear term on the D model that this also has. So therefore, for the approximation purposes, for the scenario when D model is much greater than the sequence length, then we actually ignore attention computation altogether from the computation point of view. This means that in that those kind of scenarios, you can make mistakes in terms of sharding, and you can still do well, because majority of computation which is QKV projection. No matter what you're doing in the attention mechanism, whether it's a group query, whether it is MQ, whether it is multi-head MHQ, whatever attention mechanism you're doing, you have to do the projection. And similarly, so since the computation itself is dominated by that, so these recipes will still work well. When the sequence length increases and the attention mechanism computation itself starts to be significant, then you have to think carefully about what it is and how you can optimize it. So for those scenarios, people have written custom kernels. XLA has some out of the box, certain compiler arguments that you can use, which can trigger more optimal implementation for your attention based on your sequence length and D model and other constraints as well. And then finally, you have custom kernel in the XLA land. Also, if nothing else is meeting your goals, then you have to use custom kernels.
I think the second question is related sequence length, right? So I still want to know, maybe help me clarify.
Yeah.
Right.
Yeah,
So the Sanity is
can I pause you for a second? I think maybe because we are holding other people on as well. So can we stop recording and discuss this? I mean, continue to discuss this offline.
Yes.
Okay. And people online, feel free to stay if you like, and otherwise feel free to drop, and be happy to discuss.
We can do now.
Yeah.
Yeah. Okay. So
Thank you, everyone.
Nice session.
you.
Yeah. Thanks.
Super helpful.